Before the transformer, processing sequences like sentences often meant using recurrent or convolutional networks. But what was the core problem these models faced, especially with longer sequences?
Exactly, Maya. Previous models, what this paper calls dominant sequence transduction models, are based on complex recurrent or convolutional neural networks, struggled with capturing long-range dependencies efficiently and were inherently sequential. The authors proposed a radical shift. They state, "We propose a new simple network architecture, the transformer, based solely on attention mechanisms." This was their audacious claim that attention alone was sufficient.
Wait, solely on attention mechanisms? We talked about attention in case number TCM 153002. Is it the same mechanism, just pushed to its extreme, or something new entirely?
It's the same fundamental idea of attention, but applied in a completely novel architectural pattern. Crucially, they achieve this by dispensing with recurrence and convolutions entirely. No more sequential processing, no more fixed-size local windows.
So it processed the entire sequence at once? That sounds like a major departure. What did that allow them to do that RNNs or CNNs couldn't?
The biggest immediate benefit was efficiency. By removing recurrence, operations could be performed simultaneously across the sequence. This made them more parallelizable and requiring significantly less time to train.
So the all you need wasn't just about effectiveness, but about computational gains too. It wasn't just good enough, it was better and faster.
Exactly. The paper demonstrates this with machine translation. They show their models were superior in quality while being more parallelizable, setting new state-of-the-art benchmarks on key translation tasks.
Impressive. So not just theoretical, but real-world performance improvements on complex tasks like English to German translation. That's a strong case for a new architecture.
Indeed, on WMT 2014 English to German, they achieved 28.4 blue, improving over the existing best results by over 2 blue. This wasn't a minor bump, it was a significant leap forward.
It reminds me of the leaps we discussed in case number TCM 063001, where finding flatter minima significantly improved generalization. Here, it's an architectural shift driving the improvements.
And the authors weren't shy about its broader potential. They conclude by stating, "We show that the transformer generalizes well to other tasks." This hinted at what would become its most profound impact.
So a new model that's faster, better for language, and generally applicable. That sounds like a powerful foundation to build upon. But how does this attention-only model actually work?
That's the core question. To really grasp it, we need to pop open the black box and see its major components. It's simpler than you might think at a high level.
Okay, let's look inside this transformer and see what makes it tick. I'm eager to understand the secret behind its efficiency and power.
Let's start by looking at the model as a single black box. For machine translation, you put in a sentence in one language and it outputs the translation in another. Simple, right?
Right, that's what any translation system does. But the magic is usually in what's inside that box, especially with neural networks.
Exactly! This article helps us by showing an encoding component, a decoding component, and connections between them. It's still an encoder-decoder architecture at its core.
So it's not totally alien then. The input gets encoded into some representation, and then that representation is decoded into the output sequence. Standard stuff.
Yes, but with a twist. The encoding component is a stack of encoders, typically 6, though the number isn't fixed. Each encoder processes the output of the one below it, refining the representation.
A stack of them, like layers in a deep neural network. So information flows up through these encoders, each adding to the understanding of the input.
Each encoder, in turn, has 2 main sublayers. First, the input flows through a self-attention layer, a layer that helps the encoder consider all parts of the input sentence together.
Self-attention again. So it's not just paying attention to the input, but paying attention to itself, the relationships within the input sequence.
Correct. After self-attention, the outputs are fed into a standard feed-forward neural network. This network is applied independently to each position in the sequence.
Independently? So the feed-forward part doesn't see relationships across the words. That seems to contradict the whole point of sequence processing. I bet many people miss this distinction.
You're right, Maya. This is a common point of confusion. It's a crucial distinction. The article notes, the word in each position flows through its own path in the encoder. The self-attention layer creates the dependencies. Then the feed-forward processes each word's enriched representation. This allows for massive parallelization, as the original paper highlighted.
I see. Self-attention gathers context, and the feed-forward network then individually processes each word's enriched representation. This allows for massive parallelization, as the original paper highlighted.
And it's not just these layers in isolation. Critically, after each sublayer, the self-attention and the feed-forward network, the transformer uses two important architectural choices. It employs a residual connection around each of the two sublayers, followed by layer normalization. These help stabilize training and ensure information flows smoothly through the deep network.
So the output of a layer is added to its input and then normalized? That's a common trick to prevent vanishing gradients in deep networks, like we saw in ResNets.
Another crucial element, since self-attention processes words in parallel and isn't inherently sequential, the transformer needs a way to understand word order. This is solved by what the original paper refers to as add positional encodings to the input embeddings at the very start. These are mathematical vectors added to the word embeddings that tell the model the absolute or relative position of each token in the sequence.
Ah, that makes sense. Without that, dog bites man would be indistinguishable from man bites dog. So, the positional encodings give it the sense of sequence that RNNs intrinsically have.
Now let's briefly look at the decoder. It's similar to the encoder with self-attention and a feed-forward network, but it has an additional third attention layer, which this article describes as an attention layer that helps the decoder focus on relevant parts of the input sentence. This is often called encoder-decoder attention or cross-attention.
So the decoder's self-attention looks at its own generated output so far, but the cross-attention lets it look back at the entire input sequence from the encoder to make sure the translation is consistent and accurate. Clever.
Think of this classic example. The animal didn't cross the street because it was too tired. To correctly understand it, the model needs to link it to animal. Self-attention helps it associate it with animal.
That's a great illustration. Without self-attention, the model might just see it in isolation. It needs to dynamically reference other parts of the sentence to resolve ambiguities.
Yes, this article clarifies that self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing. It's how context is dynamically incorporated.
So, unlike an RNN's fixed hidden state that accumulates information sequentially, self-attention allows each word to look at all other words simultaneously for context.
Precisely. That simultaneous dynamic context gathering is key. But how does this looking actually happen? What's the mechanism behind self-attention itself? That's where Q, K, and V come in.
Okay, the query, key, and value vectors. I've heard those terms before. Let's dig into how those three pieces construct this dynamic context.
The first step in self-attention is to create 3 specific vectors for each word in the input: a query vector, a key vector, and a value vector. These are derived by multiplying the word's embedding by 3 distinct learned weight matrices.
So every input word simultaneously generates a query, a key, and value. What do these different rules represent in the process?
The article calls them abstractions that are useful for calculating and thinking about attention. Think of query as what you're looking for, key as what's available to be found, and value as the information associated with what's found. This analogy is helpful for intuition, but remember, it's an abstract mathematical operation on vectors, not a literal search. The finding is probabilistic and continuous, not a discrete, exact match.
Like a database lookup, I have a query, I search against keys in the database, and if there's a match, I retrieve the associated value. Is that a good analogy?
It's a good starting point, Maya, but let's be clear on its limitations. In a database, you get an exact match, or a set of exact matches. Here, we're calculating a degree of similarity between every query and every key, and then using all the associated values, weighted by that similarity. It's more like a fuzzy, weighted retrieval from every item rather than selecting just one.
Okay, that clarifies it. So it's not a hard yes or no match, but a continuous spectrum of relevance for every other word.
The second step is to calculate a score for each word. For a given query, we compare it against all the keys in the sequence.
So if I'm processing it and it's my query, I'm comparing it to the key of animal, the key of street, and every other key in the sentence?
Precisely. That comparison is done using the dot product of the query vector with the key vector. A higher dot product means the query and key are more similar, indicating stronger relevance.
Dot product for similarity makes sense. It's a common trick. So this score quantifies how much each word in the sentence matters to the current word we're encoding.
After scaling the scores by the square root of the key vector's dimension, often square root of dk, to help stabilize gradients during training, the next critical step is to pass the result through a softmax operation. This converts the raw scores into probabilities, or attention weights.
Ah, like a normalized distribution. So all the attention weights for a single query will sum to 1, making it clear what percentage of focus each other word receives.
Indeed, as the article states, softmax normalizes the scores so they're all positive and add up to 1. This directly determines how much each word will contribute to the output.
Okay, so we have these attention weights. What do we do with them? How do they actually transform our word's representation?
The next step is to multiply each value vector by the softmax score we just calculated. This weights each value by how much attention it should receive. Finally, we sum up these weighted value vectors to get the output for this specific query position. This final aggregated vector is the enriched representation of our word, incorporating context from all other words based on their relevance.
So the output vector for it would be a weighted average of the value vectors for animal, street, and all other words, where the weights come from how much it pays attention to them.
Exactly. And this entire process is done in parallel for every word in the sequence. This is the core of single-head self-attention.
That's quite elegant. But I've heard of multi-head attention. Is that just doing this same process multiple times?
You're spot on. The transformer doesn't just run this once. Instead, it uses multiple attention heads in parallel. Each head has its own set of query, key, and value weight matrices. The original paper clarifies this by saying, multi-headed attention allows the model to jointly attend to information from different representation subspaces at different positions.
This means different heads can learn to focus on different kinds of relationships. One might focus on syntax, another on semantic similarity, for example.
So instead of just one overall attention, we get several distinct perspectives on the relationships within the sentence, and then those perspectives are combined. That sounds much richer.
Exactly. This multi-perspective attention, combined with the other architectural elements, creates a powerful processing block. But despite its power, every model has its boundaries.
This parallel processing and dynamic context gathering sounds incredibly powerful. But are there any downsides or limitations to this attention-only approach?
Absolutely, Maya. While revolutionary, the transformer isn't without its challenges. One significant one is its computational complexity. Self-attention scales quadratically with the sequence length. That means if your sequence doubles in length, the computation increases fourfold. For very long sequences, like entire books or high-resolution images, this can become prohibitively expensive, leading to ongoing research into more efficient attention mechanisms.
So while it's parallel and fast for typical sentences, pushing to extremely long contexts becomes a bottleneck due to that quadratic scaling.
Precisely. Also, unlike CNNs that inherently understand local structure, transformers are blind to order without additional help. That's why positional encodings are so vital. They add positional encodings to the input embeddings to inject information about the relative or absolute position of tokens. Without them, the model wouldn't know if dog bites man is different from man bites dog.
So its generality is a strength, but it means some fundamental properties, like order, have to be explicitly told to it rather than being an intrinsic part of its mechanism.
Exactly. And this quadratic scaling issue is a prime example of where research continues to build on the transformer's legacy, exploring linear attention, sparse attention, or combining it with other architectures, pushing the boundaries even further beyond the already significant.
It's always fascinating to see how even groundbreaking architectures present new challenges, driving the field forward. A clear win for attention is all you need, but perhaps attention alone isn't always enough for every extreme scenario.